You ever get a brilliant idea for an app or a game and then just stop, wondering how you even begin to tell a computer what to do? How does a thought in your head become something real, something that actually runs on a screen? Well, that's exactly what we're going to unpack today. We're going to look at the blueprint for turning any idea into action with a computer.
All right, let's kick things off with a little thought experiment. Imagine you've got this super advanced robot chef in your kitchen. It can do anything, but it's also very, very literal. So here's the question. If you wanted it to make you a peanut butter and jelly sandwich, how would you tell it to do that? You can't just say, hey, make me a sandwich. So why not?
Well, here's why. That robot, just like every single computer out there, needs incredibly precise, step-by-step instructions. It has zero intuition, no common sense whatsoever. It only knows what you tell it, and it follows those instructions to the letter. So the real trick isn't just what we want to do, but how we say it in a language the machine can actually understand. This whole journey, from our brain to the robot's action, follows a pretty clear path. It all starts with the idea, right? Our PB&J sandwich. From there, we need to create a recipe for it, which in the tech world we call an algorithm. Then we have to translate that recipe into the robot's language, that's our program. But even that needs a master translator called a compiler to make the final leap. And only then do we get the final action, our sandwich. Let's break this whole thing down.
So let's start with that first piece of the puzzle, the recipe. Now, in computer science, we have a fancier name for it. We call it an algorithm. But honestly, the idea is exactly the same.
That's really all it is, seriously. Think about your favorite recipe for chocolate chip cookies. It's just a list of very specific steps, right? If you follow them in the right order, you get cookies every time. An algorithm is just that, a clear, ordered set of steps to solve a problem or get something done.
Okay, so here's the formal textbook definition, and I know it looks a little intimidating, but let's just tear it apart real quick. Finite sequence just means it has to end. You're not mixing cookie dough forever. Well-defined means every step is crystal clear. There's no guesswork. And computer implementable just means it's something a machine can physically do. See? It's just a super precise way of saying a recipe.
And here we go. This is a perfect example of what a simple algorithm looks like. For our sandwich, the steps are clear, they're in a specific order, and if you follow them, you solve the problem of not having a sandwich. This level of tiny detail is exactly what a computer needs. All right, so we have our recipe, our algorithm, but there's a problem. It's written in English, and our robot chef doesn't speak English. So now we have to move on to the next step, translating that recipe into a language it can understand. And we do that by writing a program. In that act of translation, that's what we call programming. We're taking the logical steps from our algorithm and rewriting them in a very specific, structured language that has its own strict rules for grammar and syntax. For the AP Computer Science A course, that language is going to be Java. Now check this out. On the left, you've got our simple English recipe. And on the right, a simplified look at what that might be in Java code. You can totally see the one-to-one connection, right? Get 2 slices of bread becomes bread.getSlices2. Spread peanut butter becomes bread.slice1.add peanut butter. It's the exact same logic, just written in a different language. And that's the official definition of programming. It's just the process of creating that set of instructions. So remember this, the algorithm is the what. It's the logic, the plan. The program is the how. It's the actual implementation of that logic written in a language like Java.
Okay, so we've translated our recipe into a Java program. We're good to go, right? The robot can finally make our sandwich. Well, not so fast. There's one more absolutely critical step that happens behind the scenes. We need a master translator.
And here's the big secret, the deep down truth about how computers work. The processor, the actual brain of our robot, doesn't understand Java. It doesn't understand Python or C++ or any of these languages we write in. At its core, it only understands one thing, electricity, on and off, ones and zeros. This is what's known as machine code. So how in the world do we get from our nicely written Java code all the way down to those raw ones and zeros? Well, that is the job of the compiler. The compiler is a special program that does this one final massive translation. It takes our entire Java program and converts it into the machine code that the processor can actually understand and execute.
I love this way of putting it. The compiler really is the final bridge. It's the thing that connects our human-readable ideas to the physical, electrical reality of how a computer actually works. Without the compiler, all of our amazing programs would just be useless text files. So let's put this all together. Let's see this entire process, from recipe to reality, in action with a classic real-world example. Forget the sandwiches for a second. Let's look at some actual code. This right here is almost always the very first program a person writes when they're learning a new language. The algorithm is super simple. Just make the words "Hello World" appear on the screen. And this block of Java code is the program that gets it done. Don't worry about all the syntax right now. Just focus on that line in the middle, system.out.println. That's our main instruction.
And when we run this program, meaning we give it to the compiler translates it to machine code, and the processor executes it, boom. This is what we get. The computer followed our instructions perfectly.
See? That simple output on the screen, it's not magic. It's the end result of that entire chain we just talked about. You had an idea. You created a simple algorithm. You wrote that algorithm as a program in Java, and then the compiler translated it so the computer could execute it. Every single piece had to work together. So, what you have now is the fundamental blueprint for how we communicate with computers, how we bring our ideas to life. It's this powerful combination, a logical recipe, a precise language, and that all-important compiler to bridge the gap. You have the keys. So, the only question left is, what recipe are you going to write first?